How do you pronounce your name? Yeah,
Clark Brzozowski.
Brzozowski, that's what I thought. That just sounds cool.
Yep.
All right, guys. Well, I speak English pretty well, and I'm fluent in Spanish, and I speak a little French. Que yo hablo un poco de español.
I knew it. I knew you said that. Could we review chapter 4 a bit more? Because I'm doing the practice right now, and there's a couple of spots where I'm confused as to how to do it.
Okay, yeah, absolutely. Anything particular in chapter 4?
Let me go back.
There's a lot in chapter 4.
I know. That's why I'm like, a little nervous. Okay, so, I know I have a lot of background noise right now. Sorry.
That's okay.
On number 1, I got most of it right, but I missed the functions decreasing on the intervals and the range.
Okay, and that's on number 1 on the review?
Yes.
Okay.
I drive a 1500 Silverado, and that's, yeah, the 1500 gets to it. Yeah, 2500. It's nice when you need all something. Yeah, I went from a 6.6.
Oops. Mm.
Yeah, but the diesel has to give you plenty of power. Yeah. And then kids and I would go up there.
Copy that over.
Say a little bell on gas on the way up there, right?
Okay. There we go. So consider that function. It's a nice polynomial. Looks like it's a 3rd degree, probably. It has a general rise to it, so it looks like it's got a positive lead coefficient. Bunch of stuff we can tell just by looking at it. Has a relative maximum. Relative maximum looks like it's there. So has a relative maximum of, remember, of means the value, so the function value. So it has a relative maximum of 6. Where is it occurring? It's occurring at x equals 0. So the relative maximum is happening at the point 0, 6. But that relative maximum output is an output of 6 happening at x equals 0. Not what you would ask, but let's look at all of it, right? Has a relative minimum. Down here, that relative minimum value is -2. It's happening at what looks like x equals 8. The function is increasing on some interval, so it's increasing. Remember, when we talk about increasing, we're talking about what x values make the function go up, essentially, as we travel in this direction. So as we travel in that direction, the function is increasing all the way from negative infinity until it reaches 0. And it's increasing from 8 onward. So it's going to be increasing from 8 onward towards positive infinity. So to put that in our interval notation, it's going to be increasing from negative infinity until 0, unioned with from 8 to positive infinity. Do take note of the brackets. At 0, it's not increasing anymore. At 8, it's not increasing. So the relative minimum and maximum points are never points of increase or points of decrease. To be a point where you're increasing, the function has to be less on one side and higher on the other side. Fair? At that maximum, it's not less on one side and greater on the other. It's less on both sides. Fair? To be decreasing, it's got to be bigger on this side, less on that side. It's not decreasing there either. That doesn't happen. So it's not in either. So those brackets should always be the open brackets, the parentheses when you're talking about increasings and decreasings. Fair? Excuse me. Where's the function decreasing? Well, it's decreasing along that range. So it's decreasing from the 0 until the 8. We'd almost want to say it's decreasing everywhere else. But again, remember, everywhere else except the 0 and the 8. So again, at 0 and 8, it's neither decreasing nor increasing. And if you think of that in terms of, say, tossing something up in the air, if the thing rises for a while and then comes to a stop and then starts to fall, right? So that for a while it's going upward, and then there's that moment that it's not going up anymore, but hasn't started to go down yet. There's that infinitesimally small moment where it's not increasing, but not decreasing yet, right? So that's that hole in the intervals. Are you happy with all that? And then domain of the function, domain and range. Remember, domain is the set of all, lots of different words we could put there. Set of all first coordinates is formal. Set of all inputs is good. Set of all x's is okay. These aren't labeled x and y, but x is kind of our default. But the set of all inputs for this function. Well, every x value, if we presume that this keeps going this way and keeps going that way, as we are supposed to presume, because there's no dot there telling us it stops, right? We'd either have an open dot or a closed dot if it did stop there. So what x values are being used? Let me get rid of all my stuff. By this graph, well, every x value has some point somewhere on that graph, right? Every x value has some output there. So what's the domain of the function? Domain of the function is all reals. As an interval from negative infinity to positive infinity. Or if you were going to write it out, you could write all real numbers. My guess is the computer wants that interval, but you could also even put this little cute little script R, the double barred R, Stands for all real numbers. What about the graph's range? Range is the set of all outputs. The set of all outputs, or y values, excuse me, or what all the second coordinates would be. Well, is there any y value that doesn't come up on the graph somewhere? Like it doesn't, we can't see the 9, but the 9 is going to end up there somewhere, right? So's 10, 11, 12, 13, 14, all the way up. All those have values. Some of these y values come up multiple times. That's okay. All the negatives, y values get used somewhere, right? So what's its range? Its range is also all reals. One of the hard things to do when you're talking about domain and range is often it's difficult to ignore things like maximums, relative maximums and relative minimums. Like the fact that this stops down here at -2, you kind of want that to affect the range somehow. But since the graph keeps going below that -2, that minimum at -2 has no effect on what our range is. This maximum at 6, if this graph didn't turn back upward, that would matter. But because this turns back upward in a way that we are supposed to presume it keeps going, again, because the lack of a dot there, then that -6 in our list of possible outputs, that -6 goes right to a 6, 6.1, 6.2, all the way up. So those mins and maxes don't have really any effect, unfortunately. Now, if the graph went, say, like that, then it would go from negative infinity up to some solid max there. Then that maximum would be not only a relative maximum, it would be an absolute maximum. That starts being a range restriction. Same thing happens, or similar thing happens with domains and x-intercepts. People often want those x-intercepts to matter in the domain, and they just don't. So Clark, I'm not sure which parts of that you were looking at, but did that that address everything that you were looking at or fighting with? Okay.
Yes, it did. Thank you.
Sure. Good. Sandy?
There's another one
Cool. What was that?
I was working on, number 4. P of x equals x cubed minus 6x squared plus 5x. And it's asking for the y and x intercepts, and as x goes towards infinity, y goes towards something.
So it's asking for intercepts and end behavior.
Yeah. So
Okay.
I got the y-intercept and the x and y infinity parts. I just don't know how to find the x-intercepts.
Okay. So let's talk about all those pieces just to be complete here. So y-intercepts, we should like finding y-intercepts. We find y-intercepts by letting x equal 0, right? So when x equals 0, we're finding p at 0. That's going to be 0 minus 0. So it's going to be 0. So we have an x-intercept at the point 0, 0. Which means we ought to have an x-intercept there too, right? So that should be natural. If we want to find x-intercepts, if we want to find all of them, we let y equal 0, or the function equal 0. So 0 equals x to the third minus 2x squared minus 48x. And we're supposed to solve that for 0. Now, a lot of chapter 4 is about solving larger degree polynomials. So the fact that that's a third degree polynomial shouldn't throw us off too much until we start thinking about our tools. Our big tool from 4.5, 4.6 would be the rational root theorem, right? Find the factors of your constant and the factors of your lead coefficient. But this doesn't have a constant that's not, at least it doesn't have a constant that's not equal to 0, right? So that rational root theorem is at least weird, if not really hard to work with. But there's a nice thing. If there is no constant term, that means every term has an x value in it, right? If every term has an x value in it, what can we do with that x? We can factor it out. And if that doesn't result in us having a constant term, well, that would have meant we had at least an x squared in everything. So factor out the x squared instead. Whatever the smallest one is, factor it out. Fair? Now, this was especially nice because it left us with a second degree polynomial, so our quadratic skills could take over. But even if that left us with a third degree, the other chapter 4 skills could then take over. Fair? So if you're ever trying to use the rational root theorem and go, there's no constant, go, yay, there's no constant, factor out an x until you have a constant, and then your other tools can take over. Fair? Now, because that's a quadratic, we should try to factor it first. If not, we can throw it into the quadratic formula, but this should be nice and factorable. 8 doesn't go there, though. I got overly excited about my 8. It would be, what, x minus 8 and x plus 6. Again, if your factoring needs practice, practice your factoring. And remember the zero product principle, each one of these makes a corresponding 0. What makes x minus 6 or x plus 6 equal to 0? Well, x plus 6 is equal to 0 when x is negative 6. This is 0 when x is 8. X is 0 when x is 0. Right? People often forget this one. So we have an x-intercept at 0, 0, which we knew we had anyway. We have an x-intercept at 8, 0, and the x-intercept at negative 6, 0. So we've got that point at negative 6, this point at positive 8. Cool. Now, the last thing to be able to draw this is to know whether or not we should be drawing it going this way, or whether we should draw it going that way, right? We know it's got to go through those points. None of those points had a multiplicity on them, so there's no bouncing or anything. But we have to know, is this thing going to go generally upward or generally downward? Is it going to be going, this way? Oops, didn't want to erase that. Is it going to be going generally this way with that little wiggle in between? Or is it going to be going generally downward with that wiggle in between? How do we tell which way it's going?
I think I probably would have just put it into the graphing calculator, and then if not that, then like one of the points in between.
Yeah, but then then your batteries die. You got to get new batteries. That kills trees and destroys landscapes. Why would you want to hurt the world like that?
Well, could you just like find a point in between the x-intercepts and then
we could, but that would take time. And if we take time to do that, then a bunny dies somewhere. We don't want to take time to do that. Though we could totally work. But what tells us without having to do any of that, whether this thing goes downward or upward?
the leading coefficient?
It was even called the lead coefficient test, right? The lead coefficient is positive, right? What does that tell us about the overall behavior of this? It's going to go upward, right? And you guys remember that was in, I think, 4.1 or 4.2, the end behavior conversations. If it was even degree, they went in the same direction. If it was odd degree, they went in different direction. It was upward if it was positive, if it was downward if it was negative. You guys remember that, right? So because this lead coefficient is positive, this thing is going to be increasing. So it's going to go that way. And that's what these questions are getting at. As the x goes to positive infinity, so as the x's go this way, what direction are the y's going? Are the y's going up or are they going down? Well, the y's are going up towards positive infinity. As our x's are going this direction, as we look at our end behavior towards the left, are the y's going upward or downward? The y's are going downward towards negative infinity. Because of that lead coefficient driving that end behavior. You're certainly not wrong, Eddie. You could have picked any point in between those and graphed it, and it would have told you where you were. You could have graphed it on camera, but that's, all we have to do is look at that lead coefficient. We have all of that information. The last thing one might want to do is figure out, well, I'd like to know how high and low those go. I'd like to know where those, we could get a very good graph of this if we just knew where that max and min was. But as I've told you guys before, that's Calc 1. And again, it's like week 3. So it's really early in Calc 1, but that is a Calc 1 skill, finding out where those are without having to approximate it on the calculator. Super easy to do too, frankly, once you learn how to do it. But yes, it's first couple of weeks. It's not hard to do. There's only one step that you guys don't know how to do, but that step again is Calc 1. So Clark, did that get at all your the little things that you were looking at for that? Or are people in your room still talking about trucks? They must still be talking about trucks. Well, what about the rest of you guys? That work? Cool. Anything you guys want to look at from either that sample or something else, or? For your last test, I sent you guys a different sample with some of videos that were going through those answers. Was that helpful? Because I do have, if you guys want, I can show you where to find those. You don't have to, they're not on my open math, they're on my my website from the department. I moved other ones over, but if you want to just grab them yourselves, you can go to faculty and departments and go to the math department. And then in the math department, go to faculty and staff and me, or you can just search my name up in the little search thing. But then under Math111, there are some sample exams. So the chapter 4 exam, you can get a sample for that. It'll download it. A PDF of the solutions. So that's the handwriting, you know, me handwriting out those solutions. And there are the videos of me handwriting out those solutions and talking through them and whatnot. So I think for exam 1, I posted the exam and the videos. I didn't post the PDF, but this has all of them. And it's got one for chapter 5 and finals. And so it's got some extra stuff if you guys want to check that out. And if you have trouble finding those, let me know. It just has some sample stuff. We did the transformation in chapter 3, so don't worry about those. But then it's got, you know, use the remainder theorem, rational zeros, building a polynomial, solving, so that's rational root theorem, asymptotes and stuff, inequalities. It's which we didn't do, so we're not going to do. So it's got some stuff you don't need, but it does have some extra problems if you're looking for those.
Could we look at number 16 on the review? I'm still having a hard time with asymptotes.
Sure. Well, that's an interesting one too. Okay. This is asking it in a fairly specific way, but why don't we go ahead and say, you know, just for completeness, you know, if we were asked to find x-intercepts, y-intercepts, vertical, asymptotes, horizontal asymptotes, as well as, you know, the restriction issues. So we'll do kind of all of those. Cool. So x-intercepts, we let the numerator equal 0. So the numerator equals 0. There's not much to do there. You know, divide by the 3 and square root, but that happens when x is equal to 0. So we're going to have a nice x-intercept at x equals 0. As long as 0 isn't also a 0 of the denominator, but if we real quick plug in x equals 0, we find that it's 36. So that is going to be a true x-intercept. So nice. To find the y-intercept, let x equal 0. When x equals 0, we get 0 over 36, which is 0. So that's again our y-intercept at 0, 0. So that's nice, except zeros often throw people off. People get worried when zeros keep popping up. But with no constant term at numerator, that's going to happen. So for vertical asymptotes happen where there are domain restrictions because they happen where the denominator is equal to 0. So that's why this question is going, hey, what are our restrictions? So our restrictions, where does our domain freak out? It freaks out when the denominator is equal to 0. And we got to solve this in with whatever tools we can solve it with. So hopefully we could factor it. What things multiply to make 36? A 12 and a 3, but I think the 9 and the 4 are going to make the 13. So 9 and 4. So your domain restrictions, x can't equal -9 and x can't equal -4. So -4 and -9 are those domain restrictions. Now, do those domain restrictions always make vertical asymptotes? No. The only time they don't make vertical asymptotes is when they also make the numerator 0, right? But we already know the numerator is only 0 when x is equal to 0. So neither of those, neither the -4 nor the -9 make the numerator 0. So both of them are going to robustly create vertical asymptotes. So we get a vertical asymptote at x equals -4 and x equals -9. Fair. Now, if we're looking for a horizontal asymptote, just to again be complete here, horizontal asymptote, we look at the degrees. The degrees match. Since the degrees match, it's going to be at the ratio of the lead coefficients, so -3 over 1, or just y equals -3. So we're going to have a horizontal asymptote there at -3. If you want to then graph it, well, we have to stay asymptotic to all these asymptotes and go through that point at 0. So that better go that way. I can't put my graph there because I'd have to have an x-intercept. So it's got to be down there. Then it's got to fit in between these, but it can't have any x-intercepts. So it better fit down there, I guess. Nope, doesn't. How do we know it doesn't? We know it doesn't because this 0 here has a multiplicity of 2, right? You weren't asked to graph this, but if you wanted to graph it by hand without having to use the calculator because it kills bunnies, right? Because that x-intercept has a multiplicity of 2, because it's got that square on it, this is going to go like that, which means this is up here, just doesn't cross that because it doesn't have any x-intercepts. And doing that like that, particularly with the multiplicity, and it does take some practice. It is nice to know that once you get familiar with all those pieces, you can figure out what the behavior looks like just by looking at these pieces without having to kill trees and bunnies. Hope that help. What is it about the vertical asymptotes that's been throwing you off? Is it the when they exist, don't exist thing? Is it the...
I'm not sure what exactly it is. I think it's just trying to remember the steps to finding them and to knowing, because I understand once we get them, like how to find holes and stuff like that, but just getting to the point of remembering the steps is hard for me.
And I think that's one of the things that are pretty common with these rational functions is that we've got 4 or 5 different tools to use. So making sure you're using the right tool for the right question, you know. And there's a lot of that in this entire course. We work with quadratics in chapter 3. There's like, well, are we looking for the vertex? Are we looking for the intercepts? Are we looking, which thing are we looking for? And are we connecting that to the right tool? So like, okay, asymptotes. What do I need when I want to find asymptotes? Well, it depends. Are you finding a vertical asymptote or are you finding a horizontal asymptote? You know, so you've got to be real specific about what tools for what you're looking for. What else you guys working on, looking at? Sean, what about you? You got anything particular you've been playing with? You've been quiet.
No, those were the ones I had problems with, but I figured it out.
Okay.
If no one else has one that they want to work on, can I throw out another one?
No.
Okay,
No, you
great.
Sure, Hope, what you got?
Could we look at number 10 just to review multiplicities?
Sure.
Or zeros, or sorry.
To review whatever 10 throws at us.
Whatever it has on there. I wanted to look at that one. Sorry.
No problem. Okay, so here we're asked to factor this, and we're even told not only 1 0, but essentially we're told 2 zeros, because we're told that 1 will work twice. Fair? And also this question is being especially nice. It's reminding us of that 0 in the y to the 3rd. We could really just be given y to the 4th minus 18y squared plus 32y minus 15. We could be told, hey, that's our polynomial with respect to y. And somebody could just say factor it, right? when we did rational root theorem, we'd find, you know, 1 is a possible. And if we graphed this thing, whatever this graph looks like, we know at that 1, it's going to bounce because we've been told it's got a multiplicity 2, right? I don't know if it's going to bounce that way and go up, or whether it's going to bounce the other way, because I don't know where it happens to be because I haven't looked at the graph. But we could be given this problem with less information than here is the 0, here's its multiplicity, and don't forget that 0, right? So you'd want to be able to do this question without a lot of that. But we don't have to, because they told us that that 1 has a multiplicity. Again, graphically, that means that at 1, this thing bounces, right? Again, I don't know if it bounces as it goes upward or if it bounces from down below. I don't know. I'd have to look at the graph or finish this problem. That would tell us too. But in terms of factoring the whole thing, it tells us when we do our synthetic division with our 1, our 0, our negative 18, our 32, and our negative 15. Since we're told that 1 is a 0, it should work perfectly and give us a remainder of 0. And we should check that. So 1 times 1 is 1, add together 1, 1, negative, what, 17 times 1 is negative 17. Add those together, get 15, 15, 0. Okay, good, it worked. We knew it was going to work unless they were lying to us. But we've also broken this 4th degree polynomial down into a 3rd degree polynomial down here, right? So we know one of the factors is x minus 1, great. But we also know because that has a multiplicity of 2, it should work twice. Because we can't really do much more without either going to rational root theorem or getting down to a quadratic. And we're not at a quadratic yet. So the fact that it told us that 1 has a multiplicity of 2, it allows us to know that the 1 works twice, and we can repeat this process. And that gave us a 0 again. It better have, because it's, you know, what we were told it's supposed to be true. And confirms that that x minus 1 is happening twice, which you can either write as x minus 1 squared or as x minus 1 times x minus 1. X minus 1 squared is really a better way to write it. But now we're down to this quadratic, this nice x squared plus 2x minus 15. And ideally, that should be something that we can factor. Fair? Because it's a quadratic. And even if it's not factorable as a quadratic, we could use a quadratic formula to figure out what the zeros would be and turn those zeros back into factors. So even if it wasn't strictly factorable, we could force it. But that would be what, a 5 and a 3. The 5 would have to be positive, the 3 negative. So that's going to give us an x equals 3 and an x equals negative 5. Now, we didn't really want those, but I wanted them because I wanted to know which of these graphs it was. And I thought it was this one. But nice to know. But our factors are x, what, minus 3 and x plus 5. So we did a little more than necessary because we weren't asked to do either of those things. But you were asking about multiplicity in general, and that's some of the implications of multiplicity. Just the fact that we get that nice bounce, the fact that it means it will divide out multiple times. Hope to help.
It does, thank you. I think I just have a hard time with remembering like math language, and that's why I get messed up.
Well, hopefully one of the things you guys are all kind of seeing as we do this, depending on what kind of math background you have, is that there is a lot of vocabulary, and that vocabulary is really important in mathematics. It's really easy to undervalue the importance of vocabulary in mathematics. We think of, in biology or chemistry especially, people are like, yeah, vocabulary, you gotta know the vocabulary. But in math, people tend to underemphasize vocabulary, and it's really a shame. The stronger your notation and your vocabulary is, the easier you will find everything else. So this is a good time to kind of be focusing on those things. And then the nice thing, one of the nice things, is the vocabulary that the math vocabulary carries into a lot of those other fields. So even if you're not going to do a lot more math, but you're going to go into business or sociology or statistics or any of the other kinds of sciences, because those are based in math tools, the math language overlaps a lot. And anyway, as mammals, we are creatures of language. Lots of how our brains work is based on languages, primates, people. So the more you can bring your language center into how you think about your math, the more tools you have for it. To make a slight segue into brain biology, the two biggest single-use areas of your brain are your occipital lobe, big chunk in the back, and your language center, which is a big chunk about there. Both of those are fairly good sized. The part of your brain that's really specific to doing mathematics is right about there, between those two lines, and it's about that big. It's about a cubic centimeter. It's fairly small in everybody. If you want to get better and stronger and faster with your mathematics, it's not about making that little chunk bigger, because it's not going to get bigger. It's about wiring that chunk to other parts of your brain, using the power of those other parts of your brain. So the more you can bring the visual cortex in with graphing and diagrams and that sort of thing, you bring the power of the powerhouse of your brain. That visual cortex is an immensely powerful part of your brain. So the more you can think visually with this stuff, the more you can bring that thing's power into your math. Your language center, the vocabulary, and the more you can get good with that vocabulary, the more you can use that language center, its power to do those mathematical chunks. When all those three things are working, the biggest tools in your brain are getting your math done. But you see a lot of students in math who go, I don't like drawing the diagrams. I don't want the vocabulary. I just want to know how to do the math. And they're really saying, I want to use just that little tiny chunk to do my math. I don't want to use anything else. And that's hard. It'll start to smoke after a while. You see often documentaries about those people who you can just ask them, what's the square root of 598? And they will list it off. I can't even get close to doing that, but they will just list it off to 100 decimals if you want, right? Those horrible, horrible people. And they often say, if you ask them, how do you do that? They'll tell you that they don't really know how they do it. They can just see it. And that is surprisingly apt, because often what happens in those people is they are just born in such a way that their math coprocessor is hooked up to their visual cortex. It's hardwired together. Most people who have some sort of savant type of skill, they can just, play the piano from the age of 5, just without any effort whatsoever. And they will tell you they could just see it. And it's really because they've got part of their brain mapped to their occipital lobe, because the power of that occipital lobe is crazy. If we could just hardwire everything to it, we'd all be crazy. But the more we could wire those things together, every time you draw a graph or a diagram, you are adding a connection between that math center and that visual cortex. Every time you draw the diagram of the multiplicity, you are connecting the language coprocessor or the language center to the occipital center to your math center, and adding that circuitry between to use all the power of those things together. Fair? So diagrams and vocabulary. Also, we can talk to each other and not slam into trees. Use it. That's my little speech on drawing diagrams and using the language. So before you guys wander off today and try not to ram into trees, what else can I do? Or are you guys good? Just need to go play with stuff. All right. Go off and play with stuff. If something comes up that you guys need, let me know. Let's see, you guys are supposed to be doing that test today, right? Okay. If that gives any trouble or you have any trouble with the scratch paper things, let me know. If not, have a good day.
Thank you.
You're very welcome.